Good evening, everyone. Welcome to the February meeting of the Popular Astronomy Club. To welcome those of you here at the Butterworth Center and a few of those who have logged online on Zoom. I see at least a few from some other astronomy clubs are attending tonight too. Welcome you all, and I'd like to welcome. We have a guest visitor tonight, Nate, here with us, Butterworth. A long-time interest in astronomy and decided to come and see what it's all about tonight. I want to remind those of you online to mute your microphones as we start here. We will be going straight to the feature presentation tonight in just a minute or two. So if you have questions, you can use the Zoom chat function, and there will be time for questions and answers at the end of the presentation tonight too. Tonight, we will be hearing from Chuck Allen as he presents perspectives on distance. After that, we will review the Popular Astronomy Club activity calendar for the year. We will have member observations as much as we have time for, and we'll be ready for announcements and adjournment. Tonight, our feature presentation. Recent technology improvements in astronomy have enabled astronomers to see more distant objects in the universe and see farther back in time. This is therefore a good time to review the scale of the universe. Tonight, we have Chuck Allen to present perspectives on distance. Chuck will examine distances from those reachable by spaceflight to what can be seen with professional telescopic observation. We will hear about the astrophysicist's current thinking on the biggest questions about the universe. How far can we see, and how big might the universe be? Chuck is the current and past president of the Astronomical League and has given more than 550 public presentations to schools, universities, scientific societies, conventions, and other public audiences. He is a LEAD gold level master observer with 43 programs completed and received both the G.R. Wright Award and the Master Outreach Award. Chuck coordinates 3 League observing programs, co-chaired the Alcon 21 virtual, and founded the League's National Young Astronomer Award in 1993. He is also the current program chair for the Evansville Astronomical Society, past president of the Louisville Astronomical Society, and a past judge and lead judge for the Intel, now Regeneron International Science and Engineering Fair. He has been an amateur astronomer since the age of 7. Chuck, we welcome you to the Popular Astronomy Club tonight. I will turn off my sharing, and it should be available to you to share your presentation tonight. Welcome,
Fantastic. Chuck. Thank you, Dale, and thanks, everyone. First of all, I just want to start off by thanking the Popular Astronomy Club, because you are, as you probably know from your own written history, one of the 13 original clubs that signed and brought into existence the Amateur Astronomers League of America, which was the predecessor name for the Astronomical League. That occurred in November of 1941, and I think you know what happened the following month. So things got sidetracked a bit during World War II, and then we formed again. And again, you were a charter member of the League. To the best of my knowledge, you're one of only 3 clubs of those charters that has been continuously a member since then. That's 84 years worth. And to say that we appreciate that is a grave misunderstatement, believe me. Understatement. You have contributed toward the growth of the League, which is now at 25,000 members, the largest it's ever been. And we're deeply appreciative of that. With regard to the program tonight, there may be a few members here at least one, who may have heard this program when I presented it in nearly the same forum up at the Cedar Amateur Astronomers Club in Iowa, but hopefully not too many will this be a repeat for. So I'll get right to it, and we'll start sharing here. Okay.
Oh, there we go.
How's that look?
Looks good.
Looks good? Okay.
See it.
So what I want to do is just start with something that confuses some people who start out in astronomy, and that's the fact that we don't always use light years to measure things. Although I'll be speaking in terms of light years entirely tonight, because that's what most people are comfortable with. But I would like to visit the idea of the parsec, which professional astronomers use. And specifically, that is the distance from which one astronomical unit, the distance between the sun and the earth, seen at a distance, would subtend an angle of 1 second of arc. It's about 4/5 the distance to Proxima Centauri, that distance. And it doesn't really matter what angle you view the Earth's orbit from to get this 1 AU, this 1 astronomical unit. As you see below, if you simply observe the Earth when it's furthest from the sun at a great distance, it will always subtend the same angle. And so that's 1 parsec, and it's about 3.26 light years. And many of you will read articles where professional astronomers speak in terms on cosmological scales of the megaparsec, which is 1 million parsecs, or 3.26 million light years. A megaparsec's a little bit further in length than the distance between the Milky Way and Andromeda, which is, of course, about 2.5 million light years away, or about 15 quintillion miles away. Okay, I'd like to drop back to the first league convention that I went to in 1965. This was held in Milwaukee, and people, amateur astronomers, dressed a little differently then than they do today, as you can probably tell. And in the center, you see me, and just to the left of me, as you look at the picture, in the somewhat checkered coat right here, is Richard Gott, friend of mine since he was 12 and I was 11. Pardon me, I've been battling a bit of a cold. So we took the train up to Milwaukee, and when we were at this convention in Milwaukee, the altitude record, the human altitude record, was 295 miles. That had been set a few months earlier by the Voskhod 2, by 2 cosmonauts, Alexei Leonov and Pavel Belyaev. And of course, this was the famous flight in which Leonov did the first ever EVA from his vehicle. And within just 5 years of this convention that Richard and I attended, just 5 years after this record was set by the Russians, we had extended the human altitude record by a factor of 1,000. And that was set on tax day in 1970, when the Apollo 13 astronauts aboard their wounded craft did a figure 8 around the moon on the very day when the moon was at apogee. And as a result of that, they got farther from the surface of the Earth than any other vehicle, any other human has ever been, 249,205 miles, almost exactly 250,000 miles. The sad thing about technology sometimes is that it doesn't always grow exponentially, because in the 55 years since then, it's still the human altitude record, 250,000 miles. We haven't improved it yet, but we're trying to. There are efforts afoot, of course, Elon Musk being at the head of that line, to try to get to Mars. And that is a task because it's a bit further away. Now, Mars gets within 34 million miles of the Earth, and at many times is as far away as 250 million miles from Earth. So the question you might ask yourself is, well, where will we try to intercept Mars when we go there? Now, it would seem logical that we would try to intercept it as it's coming around toward opposition, head directly out and meet it here, just a short 34 million mile jaunt. But there's a big set of problems associated with that. The first is you have to undo the orbital speed of the Earth around the sun. That's 67,000 miles per hour. That's almost 2.5 times the escape velocity from the Earth. So not only do you have to escape the Earth, but you have to undo this incredible amount of speed in order to go straight out and meet Mars. And that takes a world of fuel. The second problem with it is if you go straight out, you're climbing straight out of the gravity well of the Earth. It's like going straight up the side of a mountain instead of zigzagging across the face of the mountain, which is much easier, more time consuming, but easier. So these two things make this kind of a flight impossible. So what we have to do is not meet Mars when it's 34 million miles away or so, and certainly not 250, but actually worse. We're going to take an over 300 million mile journey to Mars, where we use the speed the rocket has as it sits on the launch pad. That's 67,000 miles per hour. The minute we lift off, we've got that speed. So we just do a little boost outward and we intercept Mars 9 months later. This is called the Hohmann transfer orbit and is the most fuel efficient trajectory to get to Mars of all. Here again, we just lift off the Earth, using the Earth's velocity to carry us slightly further out. And then we'll let Mars pull us in from behind as we get near it, right toward the end of the trajectory here, about 300 million miles. Well, this discussion might lead you to wonder, what's the closest that any planet gets to us? Or what is the closest planet to us? Those are two different questions, because the closest any planet gets to us is clearly Venus. It gets as close as 24 million miles from it. But if you ask the question, what is the closest planet to us, it becomes fuzzier, because in point of fact, Mercury spends far more time closer to us than the other two planets do, of the inner planets. It averages just 97 million miles from us and spends 47% of any lengthy period of time, say 5 years, being the closest planet to us, far more than either Venus or Mars. Well, then we have Voyager. Voyager 1 is the furthest space vehicle we have ever placed into space. It currently resides 15 billion miles from Earth. That's about 5 times further than Neptune. It's taken 48 years to get there and is so far out now beyond the sun's influence, the heliopause, that it's traveling at 38,000 miles per hour and not slowing down much at all. So one might ask a question, well, what if Voyager were headed toward the nearest star to the sun, Proxima Centauri? It's not, but what if it were? How long would it take to get there at this incredible speed, 38,000 miles per hour? After all, it's gotten 5 times further than Neptune in just the 48 years that it's been moving. The answer is it would take 75,000 years to get there. Now imagine the size of a spacecraft you would need to support humankind for any lengthy journey, with doctors and cooks and caretakers and engineers and astronauts. It would be an extraordinary amount of size that you would need, and just to get such a vehicle up to 38,000 miles per hour would be a task. Many of you, when you go observing in the summertime to dark sky sites, get to enjoy a view like this as you look to the southern sky in Sagittarius. You see the nuclear bulge of our galaxy, but how far are you actually seeing when you look at this? And the answer is, what you are seeing is you're looking from our position in the Orion spur of the Milky Way galaxy, and your view is being occluded by the Scutum Centaurus arm of the galaxy, about 10,000 light years away. So what you're actually seeing when you look at those star clouds in Aquila and Scutum and Sagittarius, you're looking at over a distance with the naked eye of about 60 quadrillion miles, about 20 million times further than Neptune is from us. As we look further out, we see 2 major companions of ours in our local group of galaxies. Andromeda, of course, 2.5 million light years, and M33, the spiral and triangulum, at about 2.7. And what we have here are the 6 largest galaxies in our local group. We're the second, of course. there are some studies that think because of excess dark matter that we may be almost as massive as Andromeda, although the current listing, as you can see, is slightly less. M33 would be the third largest galaxy in our local group, which contains about 55 galaxies altogether. There's a galaxy in Hydra that comes in fourth, and then our Magellanic Clouds come in fifth and sixth, so they're quite substantial. As we look at the local group, this is pretty much how it's oriented. Our Magellanic Clouds, the Milky Way, Andromeda, and a huge cadre of about close to 40 companions, and M33. So the question one might ask is, well, just how do we get a handle on how far away Andromeda is? And this is where Richard Gott comes up again. He's going to come up several times in this, my friend who is an astrophysicist at Princeton that I showed you at the convention in 1965. Apparently, I was having dinner with he and his parents over at his house one night. And
not get in.
Not that I know of.
I'm hearing some background talk.
Shit.
Yeah. Okay, thank you. So I was over at their house, and apparently I said something because the following year I went over there for dinner when Richard was in town from Princeton, and Mrs. Gott, his mother, had a garbage bag in the middle of the dining room table. Now, this was a garden club president, so this is not a normal thing to have in the middle of a table for her. But it was quickly unveiled, and what was revealed to me was this. It was a bowl that answered my apparent comment from a year earlier that I wished I had 1 million of something so I could show people when I give talks just how big a number that is. And she had obtained, scientifically measured, a bowl with 1 million beads in it. And so I thought I would do a little quick calculation in my head and try to figure out how many bowls of beads I would need to have enough miles, if each bead represented a mile, to account for the distance between the Milky Way and Andromeda. So we have a 1 foot wide bowl here with 1 million beads in it. So if we lined up bowls side by side, how many would I need in order to get enough miles to get to Andromeda from here? Well, the answer is, of course, there are 1 million beads in 1 foot. Over a mile, you would have roughly 5 billion beads, 5,000 times as many, 5,000 million, 5 billion. Well, the distance to Andromeda is 15 quintillion miles. That's 15 billion billion divided by 3 billion yields 3 billion miles of bowls. A line of bowls 3 billion miles long in order to have enough miles to get to Andromeda. It's not close by. As we shrink that distance to a much smaller distance between the Milky Way and Andromeda, we find ourselves at the end of a long tentacle of galaxies. It's called the Virgo supercluster, with the Virgo cluster at the head of it here. And this tentacle of galaxies, of course, causes us to see lots of galaxies that are bright as we look in this particular direction, but not in other directions, as we'll see. So there are lots of familiar faces in this tentacle. We have close by NGC 253 in Sculptor out here. We have the NGC 5128, which is the Centaurus A radio source galaxy here, pretty close by. We have M81 here, M101 here, the Sombrero galaxy here, M51 roughly here. So these are all bright galaxies that we see mostly as we look toward Virgo or toward Ursa Major in that region of the sky. And it covers a distance of roughly 60 million light years as we look toward the Virgo cluster. Now, as you look into the Virgo cluster itself, you see this. The black spots are blocking out stars that would otherwise create a lot of glare for you. And so you see some familiar faces here. You see M84 and 86 in this famous quintet of galaxies here. The famous eyes here. This is all part of Markarian's chain, and the huge galaxy at the very core of the Virgo cluster, M87. And for a little scale, I'll show you how big the full moon is compared to this. It's a pretty large area of sky and just loaded with bright galaxies as we look toward that Virgo cluster. If we back out to about 250 million light years, we begin to see another structure that's called Laniakea. And this is a Hawaiian word that means immeasurable heaven, except we have measured it. It's about 250 million light years across. And we begin seeing, unfortunately, it's hard to envision 3 dimensions in a 2-dimensional image like this, but we begin to see voids surrounding us, long chains of galaxy clusters, but also connected voids. And as we look from the Milky Way here out toward NGC 253 and Sculptor, the reason we don't see many galaxies in that direction is because we're looking into the Sculptor void, an area that's almost completely empty of galaxies. And those of you who have ever tried to observe galaxies in Boötes know that they're all faint because you're looking across the Boötes void at them. So they're all far away, unlike looking toward the Virgo cluster. If we back out even more, we begin to see that Laniakea is part of a giant swarm of galaxies that are all flowing towards something called the Great Attractor. And if we back out a bit more to about 1 billion light years, the Great Attractor would be here, the Virgo cluster here, our location right here in this yellow area. This is Laniakea up here. But we see these chains of galaxies and these voids extending to great distances from us. And if we back out to 10 billion light years width, we begin to see the cosmic web, this incredible structure that's somewhat like Swiss cheese. That is, if you had a Swiss cheese, and you were a bug, you could eat your way all the way through the cheese block, or you could fly through the holes because they're all connected. The holes are connected and the chains are connected. So who came up with this idea? Well, it was first postulated in a paper postulating the sponge-like structure of the universe in 1986. And who came up with it? It was my friend Richard Gott. And when he was at Princeton University in 1986, he was the first to do so. And he has written a book called The Cosmic Web as well. So how far can we see as amateur astronomers? You'd be surprised at the incredible depth to which you can observe with amateur instruments. This one, 3C273 in Virgo, shines at magnitude 12.9, easily seen in small telescopes, but it lies at 2.43 billion light years. This is actually the hottest known place in the universe currently. The accretion disk that is surrounding the black hole that is issuing all of this radiation that allows us to see it so brightly over such a huge distance measures in the trillions of degrees. And once you find this little V-shaped formation, you just look for the little star next to a star in the V, and you've got it. But you can do much better. This is my favorite target, easily again seen in a 10-inch or a 12-inch telescope that can reach magnitude 14.6 in good skies, because it's in a field with 2 8th magnitude stars that form a little triangle here. And once you find that, you're home free. You just look for a triangle of 11, 12, and 13 magnitude stars here, and then look for a little arc of 14th magnitude specks right here. And bingo, when you see that one, you're seeing a quasar called PG 1634 plus 706. And wow, are you seeing across a huge gulf of space here. Light travel distance is 9.6 billion light years. And today, in whatever form that galaxy has now, it's 12, almost 13 billion light years away, because the whole time this 9.6 billion years was passing and the light was heading to us, the universe continued to expand, separating it to a distance of nearly 13. Now that means that you're seeing an object here that is 2 trillion times further. The light has traveled 2 trillion times further than the distance between us and Neptune, and 200 million times further than the distance between us and Proxima Centauri. And again, you can see it in a small telescope. This is roughly what you're seeing. It was here when the light left there, about 9.6 billion light years away. And as the light traveled to us, the universe expanded, and today it's out here at 12.9. You are literally seeing something whose light has passed completely across most of the detail of this cosmic web that you see in the image. And there are hundreds of thousands, millions of galaxies represented in these tendrils that you're seeing. And you can do even better. most amateurs, somebody in the club is bound to have access to an 18 or 20-inch Dob. And with a little careful charting, you can find your way to APM 08279 plus 5255 in lengths. This shines at magnitude 15.2, so you will need a fairly good-sized telescope for this. But when you see it, you will be stopping photons with your eye that have been traveling to you for 12 billion years in a universe that's only 13.8 billion years old. Today, in whatever form this quasar has become over those 12 billion years, it lies at a distance of 23.6 billion light years. This photograph was taken by a good friend of mine in Evansville. Well, lately, there's been kind of a battle going on between the Subaru telescope, the HST, and the James Webb to observe the furthest thing that we can possibly observe. And we're pretty near the limit because we're looking so far back in time now that we're looking back to a time before stars had a chance to form. It's called the Dark Age. And there's nothing to see shining if you look too far back in time. The record in 2014 was max 1149 JD1, light travel distance of 13.28 billion light years. Today, it lies at 30 billion light years, meaning that today, in whatever form this little proto-galaxy became, it's out there in a place that is being separated from us by the expansion of the universe today at over twice the speed of light. Here became the record in 2015. This held the record for quite a while, GNZ11 and Ursa Major, with a light travel distance of 13.39 billion light years. So now we're looking back to within 400 million years of the Big Bang itself. And this amazed people because we just weren't sure that anything would have been shining enough for us to see that far back in time. But the record was broken again in 2022 with the discovery of HD1 and the confirmation spectroscopically of its distance, light travel distance of 13.463 billion light years. But the current record was set just this past May when Jade's GSZ14 was discovered in Fornax. It's not this foreground galaxy, it's this red splotch from behind, whose spectroscopic study indicates has a redshift consistent with a light travel distance of 13.43 billion light years. That's the current record holder. And that means you're seeing something as it was just 400 million years after the Big Bang. Stunning, because this is thought to be well into the Dark Age. That is a point in time so far back in time that not many stars had a chance to form yet. So what if you were floating in space with a mile-wide mirror and a giant space telescope with a friend, and your friend was looking through the eyepiece and somehow could magically be able to see this optically? And your friend turns to you and says, well, how far is it? Now, you notice I have the word is in italics here because that's really a magic question. And there are three possible answers you can give to that question when you're looking at Jade's Z14. The first possible answer is about 1.1 billion light years, because that's how close it was when it looked like this. When the light left there and started on its way to us, it was about 1 billion light years away. But by the time the light got here, it had passed through stretching space-time for so long that it ended up having to travel for 13.43 billion light years. And by the time it got here, the expansion of space had taken this galaxy to a distance of nearly 34 billion light years. A way to think about this is a father taking his daughter to teach her to swim. He's told her how to do the crawl. He says, just swim to me. Do what I told you. And so we'll let Emily be the daughter. She's going to be our photon, and she's hanging on the wall here on the left, which will represent Jade's Z14. Now she looks at Dad and says, well, he's only 10 feet away, so this is no problem at all. Unfortunately, this is a magic swimming pool. The walls constantly move apart. The floor of the pool constantly stretches. Extra water is sprinkled in to keep the depth up. So she looks at Dad 10 feet away, says, I've got this. She lets go and starts swimming toward Dad. But because all of the space in front of her and behind her is expanding, She ends up having to swim 100 feet before she gets to Dad. And when she gets there and looks over her shoulder, lo and behold, the wall she left is 300 feet behind her. Well, this is sort of the case with this furthest galaxy. It was 1 billion light years away, 10 feet away when the light left there, when she let go of the wall. By the time the light got to us, it had traveled 13.8 billion light years, 100 feet. But by the time she got here, the galaxy, the wall, had receded to 300 feet, to 34 billion light years. So here's how we might diagram it. This is not perfect because this is a two-dimensional image here, and we're living in a four-dimensional universe when you factor in time, and it's a dynamic universe. But just for simplicity, imagine that this light blue area in the center here with a radius of 13.8 billion light years is the distance from which light has had time to reach us in the 13.8 billion years the universe has been around. So here's Jade's Z14. Its light travel distance has covered 13.5 billion light years. And today it lies out here at 33 or 34. Now, this yellow line here, what's that about? Well, that's something entirely different. This is called the Hubble distance. And any object on this line, 14.4 billion light years away, because of the expansion of the universe, will be separating from us at the speed of light. It's not going to be moving at the speed of light. It's simply sitting in space, just as we are, but space between us is expanding. Think of two raisins in dough that's rising. If the two raisins are far enough apart, they'll be separating at the speed of light. And that's what this yellow line represents. This will come up again in a minute. Well, where are all the other galaxies that we see? Well, this is the record holder you're looking at here. So all the other galaxies that we see are closer and have shorter light travel times to us. But if you can imagine that galaxies are evenly distributed in space, sort of like the diagram here on the left, and you start creating concentric spheres, each with the same radius, you'll notice that if there's one galaxy in the central sphere with a radius of 1, in the second sphere between 1 and 2, there'll be 7. And in the third sphere between 2 and 3 units of distance away, there'll be 19. So the further away you go, the more galaxies you see. So most galaxies that we see lie at great distances, with Jade's Z14 being the record holder. Okay, now let's imagine for a moment that right after the universe became transparent, shortly after the Big Bang, it was actually 380,000 years after the Big Bang, but that's pretty close to 13.8 billion years ago. So imagine that something had been shining then, and its light had taken the entire 13.8 billion years to reach us. That galaxy today would lie at 46 billion light years. And since that's the furthest thing that we could possibly see, the distance of 46 billion light years is called the cosmic particle horizon, but it's what astronomers refer to as the edge of the observable universe. It is the location today of the furthest possible thing that we could see today. Now, we haven't seen anything that far away because, again, 13.7, 13.6 billion years ago, nothing was shining. Nothing had formed yet. But theoretically, that would be the edge of the observable universe. Now, this is our observable universe with a 46 billion light year radius. And there are many other observable universes around. Some overlap ours, some don't. Depends on where you are. In this particular case, a person at this location could see a galaxy here that we can see, but we can't see each other. We're too far apart. We lie outside of each other's observable universe. Well, let me ask another question. What if you had a galaxy that right now was 15 billion light years away? The question I would ask is, can we see it? Notice it's beyond the point that's being separated from us at the speed of light. Can we see it? Well, sure. We can see all these, including this one that's out at 33. And the reason we can see these is because we're seeing the light that left there long ago. But what if today a supernova went off in this galaxy 15 billion light years away, and the light just now started toward us, already being beyond this Hubble distance could it reach us? Now, it seems like the answer would be no way. How can something that's moving away from us or being separated from us at greater than the speed of light ever get a light beam to us? Well, the answer is it can. And the reason it can is because the space between that galaxy and our Hubble distance is not expanding faster than the speed of light. And so it can make it inside our Hubble distance, those photons. And once they do, they will eventually make it the rest of the way. And that's true out to 16. A galaxy at 16, if today a supernova goes off, the space between it and our Hubble distance is not greater than the speed of light, separation rate, and therefore the photons can make it inside and will eventually get to us. But beyond 16, there's too much space expanding too fast for those photons to ever make it inside our Hubble distance. And this establishes another horizon called the cosmic event horizon at 16 billion light years. And quite simply, what that means is anything that occurs today beyond 16 billion light years, we're never going to see. That means that if a galaxy beyond 16 billion light years today sends us a radio signal, we're never going to receive it. If we fire up the Enterprise to warp 1, we're never going to get there. All the galaxies beyond 16 are said to be unreachable. Now that's kind of interesting because look where all those galaxies that we see in our Hubble Deep Field and all those magnificent photographs of galaxies are. They're all unreachable. And a point of fact, because of this, almost 97% of galaxies that we can see now are already unreachable. That means the last photons that we're ever going to receive from those galaxies in these pictures left those galaxies a long time ago. They're still streaming in, and they'll be streaming in for quite a while, so you don't have to rush out and start photographing real fast. But nothing leaving those galaxies today will ever reach us. Really kind of daunting. And of course, the expansion of the universe is responsible for this. So this is basically what we're seeing here. If you observe that APM and Lynx, that quasar and Lynx, you'll be observing a light travel distance that's roughly a third of the distance to the edge of the observable universe. And if you observe JADES, Z14 with your James Webb Space Telescope, a slightly longer light travel distance, and today it lies out into what we thought was a dark age before stars really formed and protogalaxies formed. So that leaves the question, what lies beyond and how much lies beyond? Now this, of course, is the area of theory, and the theory has to be based on something, based on observation, and the observation has been done by the WMAP, COBE, and more recently, the high-resolution Planck satellite as it examines the cosmic microwave background that you see here of the entire sky. These modelings, which are called anisotropies or temperature variations, are very telling because astronomers know if the modelings appear smaller than predicted, that would mean that we have a negatively curved universe, which would be an open and infinite universe, infinite to begin with and infinite now. If the modelings are larger than we would expect, it would be a closed universe that is likened to the surface of a sphere, unbounded as the surface of a sphere is, but finite in size. If it's flat, which the Planck satellite seems to conclude that it is within the 0.4% margin of error, that means if you erect a triangle among any three galaxies you find, at no matter what distance, that triangle will have 180 degrees in it. In that case, the universe becomes infinite at an infinite date in the future. So the bottom line is, if it's open, as most astrophysicists believe it is, or flat, which the Planck satellite seems to conclude that it is, it's basically infinite. But if it's closed, and there's still a possibility it is, then we can put a smallest possible size on the universe. And that smallest size would be 250 times larger than the radius of our observable universe. That comports with 15 million times larger in volume than the volume of our observable universe. Now, where does this 250 come from? Remember I said the margin of error was 0.4% for the Planck satellite. It says the universe is flat with that margin of error. Well, 0.4% is 1 part in 250. If the universe were smaller than 250 times larger than our observable universe in radius, we should be able with the Planck satellite to detect that curvature, and we can't. So that pretty much puts the smallest possible size if the universe is closed. Now, Alan Guth and Andre Linde did an actual calculation, and they concluded that if it's closed, it would be vastly larger than that. Guth said 300 sextillion times larger in radius than the radius of our observable universe. Linde said possibly as much as 10 to the 40,000th power times larger, and that's if it's closed and finite. So it's big, no matter what. Now, at this point, I'm going to close by suggesting that you probably feel fairly small right about now. And I want to try to cure that. As many of you know, there is the smallest meaningful distance in our physical universe called the Planck length at 1 × 10 to the minus 35 meters. It's actually 1.6. This is a distance at about a quadrillionth the size of a proton, at which the quantum uncertainty reaches 100%. Time and space become completely roiled, and our laws of physics simply don't apply. If you tried to observe something at the Planck length, you'd have to use electromagnetic radiation with a wavelength of the Planck length, which would have so much energy, it would turn the Planck length target into a black hole, and you get no information back. So if we start there and look at orders of magnitude, we find that there are about 62 orders of magnitude by 10 between the Planck length and the size of our observable universe. And the median object that lies just 31 orders of magnitude between these two are the smallest thing that the human eye can see without optical aid, dust grains in a sunbeam. So that's the median-sized object, and we come in 4 orders of magnitude larger than the median-sized object in our universe. So we're not small at all. And if that doesn't work for you, I'll conclude by showing you a little cube of tungsten I have. It's 1 cubic inch, much smaller than it looks here. And this cube of tungsten has 1 septillion atoms in it. It's actually 1.03, but we'll just call it 1. Now that is well more than 5 times more atoms than there are stars in the entire observable universe. And just to give you an idea, just along one edge, you have 100 million atoms here. So given the fact that in this little cube, you have more atoms than you have stars in the observable universe, and the fact that this cube is essentially 99.99999999996% empty space, it's really a good deal like the universe. So if you're feeling small, grab yourself a cubic inch of tungsten, hold it in your hand, point to it, show it to someone and say, universe, and you won't feel so small after all. I'll stop sharing here, and if any of you have any questions, I'll be happy to answer them. And here's that little cubic tungsten, by the way. Same density as gold, heavy as can be, amazing.
Hey, thank you very much, Chuck. I will go back to my screen sharing here. Okay, there it comes up. Okay, very interesting. A lot of insights there. How big and how small everything is. We will open it then to any questions we have here at Butterworth, or if anybody online has a question, feel free to unmute and speak up. No questions here?
There is a question. It says, the parsec an angle or a distance? A parsec is a distance. It's a 3.26 light years, but it's based on an angle. That is to say, it's the distance at which a distance of one astronomical unit would appear to subtend an angle of 1 second of arc.
Is there any variation in the expansion of space?
Absolutely. It expanded very rapidly early on and slowed. And it slowed for about roughly 8 billion years. And then magically, about 5 or 6 billion years ago, it started speeding up again. And some Nobel Prize winning research a few years back studying supernovas that were both close and far, expecting to find a linear relationship in their brightness and their redshifts, did not find that. They found that there was evidence from these supernova studies that the universe is accelerating now in its expansion. The general explanation for that is that during the early part of the universe, the gravity of the mass of the universe was retarding or slowing the expansion. But when the universe became large enough and matter was more attenuated, dark energy became the more dominant force and started accelerating the universe more rapidly, which is occurring today.
Yeah. Any other questions here? I have one comment, maybe like to discuss that. I know recently our local museum had an exhibit on the Hubble Space Telescope and also had information there on the James Webb. And it's impressive to look at some of the results from there, particularly the Hubble, where they looked at the point in space that had nothing and did a long time exposure and found many, many more galaxies out there. And then you look at a similar type of thing from the James Webb, and they say it's even further and further out. Do you think that we will continue to see further out, maybe refine some of these distances that you've mentioned tonight, if we go even beyond the James Webb telescope and have larger apertures going further out into space?
The example I would use in answering that would be Javier Sotomayor's high jump record. It was set back in the 1990s and still stands. I think it's 8 feet, ½ inch, something like that. If somebody breaks it, they're going to break it by a centimeter. And it might take decades before that happens. The point is that we're already peering so far back in time that no matter how big a space telescope you build, you cannot see anything beyond a certain point in time after the Big Bang, because there simply was dark gas at that point. It was hot, but it hadn't formed stars yet. Now we're already looking back to within 400 million years of the Big Bang. So if you look back to 300 million years, which would just be another 100 million light years further, you're into an era where we don't expect to see anything. Now, what the James Webb is finding are these red dot galaxies you've probably seen, which are very strange. They're very massive, and they don't have a good explanation for those yet. But don't be too quick to jump on these hysterical YouTubes that claim the universe is 26 billion years old and all our science is wrong, because a lot of that's clickbait and it's not based on examination of data yet. But they're working very hard to try to come up with theories that comport with what they're seeing. But in answer to your question, yeah, they'll probably break the Jade Z14 record just as they broke the ones before that over the last couple of years, but it's going to be by inches. They're not going to make a leap into, you're not going to see something 14 billion light years of travel time in the past, because the universe is only 13.8 billion years old. So there's a limit and we're near it. Now, the reason the James Webb's so good at it is because it has that golden mirror. It's very sensitive to infrared radiation. And these galaxies are traveling, the light's been traveling through expanding space so long, the wavelength of the light has been stretched so deeply into the red that we need a mirror that's sensitive to that in order to see these galaxies. So that's why the James Webb has done so well. But I think, if I can add one other comment, bigger space telescopes will allow us to see these objects in higher resolution And that's where we'll gain a lot more insight into what's going on in the early universe, I think.
Okay, very interesting, Chuck. Any other questions? Think we see anything online either from questions? I will thank you very much, Chuck. We've learned a lot tonight and have a lot to think about.
Well, it's my pleasure, and I really would love to get up to see you guys in person sometime, maybe later this year or early next year. If you have an opening, I'd love to do that. It's not that long a drive, and I just couldn't make it this time. Got a lot going on this month and the next, but after our convention, I'd like to come up there. And I've got a display I think would knock your socks off, so I'd love to bring it up.
Okay, I may be in contact with you then and see what we can work out for a future opening here at the Popular Astronomy Club.
Fantastic. Thank you.
Thank you, Chuck. Chuck, you're welcome to hang on here and look at the rest of our meeting, or you are free to sign off and we'll get to our local business.
No, I'd like to see what's going on.
Okay, well, that's exactly what my next slide is here on our Popular Astronomy Club activity calendar. We're just in the process of setting up many things coming up this year. So I just wanted to highlight a few of them that are coming up fairly soon. I don't know if my mouse is working on the big display or not, but coming up March 10th will be our next monthly meeting, and that will be a business meeting, and we will have smorgasbord talks by members. So if you like to share some of your information with the rest of the club and online here, be sure to contact Dino, and he will coordinate a schedule of smorgasbord talks, so we can have several at our next monthly meeting. Just a few days after that will be our first public observing session of the year at Niabi Zoo parking lot. And Chuck, they allow us at the local zoo to turn out the lights and set up our telescopes, and we have some very successful public programs here in the Quad Cities area at those. And this year we will also be having rain dates available for most, but not all, of the Niabi Zoo sessions. Well, as Chuck had reference here, coming up April 25th and 26th, Natural Convention in Minneapolis. That is coming up, labeled First Light, New Frontiers, New People. And Al is, of course, very active in setting that up as the president of the Natural region. A note I want to make on that, April 4th is the deadline for making a reservation to get the special hotel rate. But there's a limited number of hotel rooms available, so it be to your advantage to make that reservation as soon as possible. Other things coming up, we will then be continuing with our regular Niabi session, and mention a few minutes some of the other things that are coming up. One of them that is confirmed yet, we will have one of our biggest campground observing sessions on June 28th this year. That's at the Alidawick Campground in Hampton. And we will have the opportunity there, since it does seem the past couple years to have fallen on bad weather nights. They actually have the next 2 Saturdays available as rain dates. If we get rained out and then get rained out again, we will probably have a third chance this year to go there. Don't forget August 9th, Popular Astronomy Club picnic and meteor shower observing. Sure to get that on your calendar. One of the meetings we have confirmed so far, September 8th, At our monthly meeting, we will have Jim Kovac presenting the search for Planet 9. Searching for something a little closer than some of the distances we've seen here tonight. And our annual banquet then is scheduled for October 8th. Still have a lot of details to work out on that. Oh, yes, we have one other thing coming up. And this will be right after our next meeting. No, actually, right after, just before our next meeting. There's a lunar eclipse, March 14th and 15th. It starts around 11 o'clock. We're probably not going to have a public observing session given the late nature of it, but we may get something together on this. 11 o'clock it starts. Really, the partial eclipse starts right around midnight. The maximum will be around 2 o'clock, and it'll end almost 4 o'clock. So it's going to be an all-nighter if you want to see the whole thing, but you can at least see it up until the total if you just stay up until a little after 1:30. That's several people know that I'm in the astronomy club and asking what's the next thing to look for up in the sky. And this is one of my, I tell them this is something to look out for coming up here in another month or so. Our NIABE session should be good, at least the first ones this year, because we'll be early enough in the year. We will have Jupiter and its moons. We'll have Mars, Uranus, and also the Pleiades and Orion Nebula. And we'll still be able to see one of our favorite stars, Coriolis, at the first NIABE session. Sometime later in the year, some of these objects will be setting before sunset, so we won't get to see it. Other things that are scheduling but don't have confirmed yet. The Rock Island Library would like to have an observing session in March, April, or October. They are working on their schedule as we work on ours. And we will be having an observing session, public observing session at the River Valley District Library in Fort Myers. It won't be at the library because of limited space. We will have one there after we deliver a library telescope to them and have a little training, and it will be kind of a kickoff session at that library for their program of having a telescope available to their patrons. Okay, others that have indicated they want to have a session this year, Scott County Library Eldridge, Silvis, and the Woodhaven Lake Nature Center out in Illinois. And in September, we've been asked to come back to Riverdale schools again. So those are all in the process of being scheduled. There's several more that are pending various determinations by the host organizations yet. We haven't heard back from them. Oh, I want to make one more comment too. We have in progress here our library telescope programs, and I believe the order has been placed. Do we have a delivery date yet? Excuse me, calling me. But when that happens, we will be getting with the libraries that will be receiving those library telescopes. And we'll be scheduling training with them. And in the case of Fort Myers, we will try to set up a public observing session to introduce the public to the fact that they can borrow a telescope from their local library. Okay, I will move on. We've had some interesting observations. At least I've seen emails of people that have done that in this past month. January 17th, Al looked at some sunspots. Several others went out to the observatory on January 29th and braved the cold to get some nice observations. And Roy had a nice sunspot observation that he shared with us during the month. Okay, so, Al, do you want to put yours from your computer there? I'll stop my sharing. You can share that observation.
Okay, can you hear me okay? Okay. Can you still hear me okay? Can you hear me okay?
Uh,
I can hear you just fine.
Okay, all right, good.
okay.
I want, just mute my computer then. Just use the room microphone here. And let me see if I can make this work.
Mhm.
There we go. And now I think these are all just kind of mixed together, so I'll just start here. This was the group that we had out at the observatory, the Castle Observatory south of Milan on, I think that was the 29th of January, if I'm right on that. The two people here are the Nordics, Chris and Gary, who are the farmers that own the land out there. This is Ken Boquist in the middle, Dan Cusack next to him, and myself. And it was cold, but it was relatively warm for January. Okay. Let's see. Now this is a picture of the sun. I think this one is yours, Roy.
Could be.
It's not mine. I'm pretty sure it's yours.
The interesting to me, the thing about that is from the all the way across, it's the whole sunspot grouping is about 311,000 miles across. And as Chuck said, the Earth is moving at about 67,000 miles an hour. So if it would start at the beginning and go to the end, it would take the Earth over 4.5 hours to cross that sunspot grouping. I just thought that was kind of interesting. And it would be smaller than most of the sunspots that we see here.
Very nice. What did you use for camera?
My dwarf two, my little dwarf two camera.
What's that?
It's a small telescope, 24 millimeter lens.
Cool. Well, you don't need a big telescope to look at the sun.
Not for the sun. No.
Here's a picture that I took out at the observatory through the telescope. And Mike, you were asking me how this is done. This was taken through the Celestron 11-inch SCT, telescope that we have in the observatory, and it was with a ZWO ASI 2600 color camera attached to the telescope, and it was 30 seconds of video basically that was stacked after the fact. And when you stack it, you get a little bit more detail out of the snapshot image that you get. But you can see the red spot.
What makes it green? I mean, usually it's not that color.
I don't know.
Oh,
I'm just learning about the camera, and you can see that my image wasn't as stable maybe as it should have been. You see the moons here. You can see like another kind of ghost image next to it. I have a hunch there was a little bit of vibration in a couple of the frames. If I went back and cut those out, I could probably sharpen that up even more. But I was pretty pleased, and it only took me 30 seconds to get that. There's the Orion Nebula. And M42 is the bright one we're looking at right there. And then M43 is this one right here. So you see, really, you see M42 and M43 together in field of view. What I was doing, there's an observing challenge, I think, the Astronomical League has right now to look at some of these Messier objects that we had available to us. I think these are still available to us this month, but the ones I'm showing you are ones that were in the January list. And the only one I missed was M1, because the couldn't point the telescope that high at the point. So I'm going to leave that one for this month sometime. Here's a picture that Dan took that evening with his setup that he had, Dan Cusack. That, does anybody know what this is? Pleiades, yep. Wonderful nebulosity there. That's really a nice picture. If Dan's online.
I'm here.
You want to talk about it?
Oh, not much to say. It's Pleiades. Took it with my ASCAR FRA 500. Reduced to 350 millimeters f4. Ended up with 30 good frames that are stacked to make that image.
Nice.
If you look at that picture, Al, I'm not quite sure it's the Pleiades. I think if you take that little glob to the left there,
Over here?
no, might go one more, go further. To the right? To the right, to the right.
Oh, to the right.
Go back a little bit, right. You take that away. And I think what it is Dan's footprint coming out of the shower because it's and the toes, and he's trying to pull a fast one on us. You don't think that looks like a foot?
I don't know, you got a wild imagination.
Yeah.
Well, it is, no, the astronomers have a lot of imagination and maybe. You know, it's one step further tonight.
Denying that at all is kind of.
Yeah, would you make sure you take on game?
This is M46, which is a nice, really nice star cluster. And embedded in that star cluster is a planetary nebula. That's what you see right there. It looks like a little bubble. And that has an NGC number. I don't recall off the top of my head what the NGC number is. Like, we can find it if somebody wants to know. But if you target M46, it's right there in it.
So Al, that's that Hubble's Night Sky Challenge. That's a February object. You getting February objects too?
Okay,
I'm doing
maybe.
it too. It's cool. I'm trying to look at them visually, and I'm taking images.
Yeah, I probably grabbed this one because I could.
You could, you bet. Well, you bet.
And I'm going to go out and do the February ones. There was a couple of them I couldn't get. I missed M1 because, like I say, the telescope was not in a position where I could point it with the camera attached to the back of it. So
Yeah, very
I'll have
nice.
to find that another
Very
time.
nice. I did end up getting M1 too, but I like
Oh,
comparing them with the Hubble images. So it's a lot. That's a good activity, I think.
Yeah, it's a good activity. This one is M78. And it's not an especially beautiful image, but I got it. So I think it's an emission nebula, isn't it? I think it is. Here's M79, which is a nice little globular cluster. And here's M81, which is a very bright galaxy. This is one of my favorites. I try to grab it every time I'm out there just because it's easy to photograph. Let me see how many. That's 15 frames stacked, 10 seconds exposure on each one. So that's not particularly difficult to image if you have I mean, I've gotten this even with this DSLR. You can get a picture of this one. This is a good one. Here's Mars. And I was kind of surprised how well that turned out. If I zoom in on it, of course, it gets kind of blurry, but you can see there's a lot of detail there.
Yeah.
There's I assume that's a polar ice cap.
Yep.
And you know what this one is? Couldn't be Uranus and Neptune. Why not?
Really see a full face.
Venus.
You would see the full disk of an outer planet. You see the full disk. This is Venus. Yeah. And don't ask me about the colors. It's not, to my eye, it's not really that color, but that's, the camera's too sophisticated for me to really get, sometimes to have it be the right color. Sometimes the things turn green, sometimes they're blue. And this is an interesting one here. I've never observed this one until that night. This is C46 or NGC 2261, Hubble's Variable Nebula. To me, it kind of looks like a comet. There's a circle underneath.
Semi-circle, darn.
Oh, down here.
Yeah.
Right.
No, underneath it. Pretty close.
Oh,
Right there.
like a smile. Right
Yeah.
there.
Yeah.
That's underneath.
Yeah, that's a nose. Smile. I don't know. You're pushing the envelope here. I think that's all the ones I've got.
You have the newest one that Byron sent? Is it really-
I didn't download it. I could probably find it if you give me some time.
I can't remember what it was. It's very similar to one that I have on my new web telescope calendar for this year. And it's getting so he's almost. The pictures are almost as good as those. This is really.
The jellyfish, IC 4.3.
That was from Byron, right?
Yeah.
Is Byron on the call here?
See him on the list.
Jellyfish?
Yeah.
Oh, there you go. That's nice. Blow it up a little bit so we can see more detail on it.
Okay.
Yeah,
Should be able to.
keep going. Look at that, nice and sharp all the way down.
Yeah, I don't know how many hours of exposure.
Usually it has it on the.
Yeah, it'll tell you the exposure itself.
Were there any others from Byron?
Yeah, there's maybe one last week. Yeah.
Is it this one?
Let's try that one next.
Oh, there's that one.
Yeah.
Yeah, that's that one.
Wow, wow.
It looks like an explosion in space, doesn't it?
Yeah, but look at the detail on it.
I think there's one.
I mean,
It was like the last, there's like that big one of these.
it is a supernova around there.
It is an explosion in space.
Yeah. It is. Looks like that. So yeah,
And Byron's gonna retire, so now I can even do more.
Oh, here's another one.
Oh.
What is this? This is NGC 2174. Does that have a common name or?
I'm gonna look that.
lot of,
NGC what?
2174, that's what the label says.
The Monkey Head Nebula.
Ah, yeah, okay, yeah, it looks like a monkey head. Sure, I see it.
There's a lot of imagination. Maybe I'm the old cripple guy. That way we can look at it.
Oh, that's M1.
Yeah, we're getting one.
I don't know if I have any. Does anybody else have anything they want to show?
Hey, Al, I think I just sent you an image.
Oh, yeah? Is this Jim?
Yes, I tried to send it. I hope this,
Okay, hang on a second. I got too many windows here that I can't really see what I'm doing.
one I took a couple weeks ago, right there. Yep.
Ah, yeah.
This is one of my favorite objects.
Now, what's this one?
Now, this is NGC 1333. It's actually a relatively close, really active star forming region. You
Wow.
see a few things in there. You got dark nebulosity, you got reflection nebula, the blue reflection nebulosity, and some of those little red guys here and there. That's some like where there's protoplanets and HH objects coming around there with young stars just starting to peek out from their cloud of gas in there.
The stars being born.
What kind of telescope did you use on this?
That was, I have a 10-inch Dalkirkham. And it's
So is that
it's
like
it's a reflector.
yeah,
10-inch f5, it's an astrograph with a ZWO, I got ASI 294 mm. So I'm using filters.
Nice.
That's like 13 hours.
Wow. Wow.
I was pretty happy with it, so I had to share. Thank you.
Did you do that one night?
No, it's over 3 nights, 3 or 4 nights.
That's great. Any other pictures? That's all I got.
Okay. Well, we had a pretty good month of observing here. Okay. Well, I think that's about all we have to go through tonight.
Dale,
Yes,
maybe I didn't copy on this, but I wanted to have a few minutes of the time to present on the board.
oh, I
guess maybe I didn't send you the thing.
I didn't see anything from it
Okay,
other
well, I sent it to
than
Dale,
the sun.
Dale, and then I attached to you, but, I mean, not Dale, I mean, Mike Heaney, but I don't think he's here.
No, I didn't
Okay,
make it
I'll
tonight.
find my way up there, so if you got
Why, I will,
10 minutes and I'll be up there.
okay.
Find a lighter. Okay, if Chuck is online and I know Al is here, they're gonna know more about this than I do, so I'm gonna try to muddle through. Is that the Astronomical League and NASA have decided to have a challenge. They have a couple of challenges. The Hubble, they talked about the Hubble one. But the Parker Solar Probe is a probe that's orbiting around the sun and doing investigation of the atmosphere and solar corona. And they had a challenge. This is the second challenge they've had, where you photograph, sketch, whatever, a picture of the sun, and then you try to, the NASA will give you the estimate of where this Parker Solar Probe is around the sun. And currently, I think the closest that's approached is 3.8 million miles. So been very close, and then it goes out and will come back again. And then what you're trying to do is picture or show what the Parker Solar Probe saw versus what you saw. So it sounds simple, but it's not really that simple because you have to have the angle of where the sun is, where the Parker Solar Probe is, where the Earth is when you took your picture or drew the thing, whatever like that. So there's some mathematics involved in doing this. I was going to attempt it. I didn't, because I didn't think they'd accept my results, because what I was going to do was take a picture of the sun on the surface and then say that the Parker Solar Probe was behind it, so you couldn't see anything.
But that would have been right.
I didn't think that would fly. Some people have a little more, whoops. You know, hang on, Captain, you get that? Let me get it, appreciate it. So anyway, Al and Ken both tried this, and they both were successful in getting a certificate and calculating the distance to the, or what the Parker Solar Probe saw on the sun versus what they saw. So I think it's pretty spectacular. There's a lot of mathematics involved, wasn't there, Al?
Well, it was the way I did it, because I calculated the actual orbit.
Yeah, Al gave me, and I sent this in to get the award and everything, so. And they also included a nice little pin that Al can share with. So this is his certificate for the Parker Solar Probe Challenge from the Astronomical League and from NASA. Congratulations, Al.
You're off the pen.
You have a good grip, Al.
Good of you.
I know. And
Makes me smile.
there you go. Oh, you have it.
Thank you.
Yeah, I think it's pretty spectacular what he did.
Wow, that's nice.
Yeah, I was gonna try it, but I didn't get a chance. It was cloudy. So, well, I bet they're gonna come out with another one.
Oh, yeah.
So I think I will.
Thank you.
Somebody sent you a line.
Yeah.
What's that?
So you okay with the explanation now?
Yeah.
Okay.
Okay, well, congratulations, Al. And congratulations him too. I don't think he was, well, I didn't see his name.
Well, I don't know if you received, he wants, it's a long story, but I gotta send it.
Okay, good. Okay, now, Paul did submit the article on the Pluto to the local newspapers, but some of you have probably heard the local newspapers seem to have a major problem with their electronic systems, and most things, communications with the local newspaper are down. I think some things have been restored. I did get a newspaper today. Getting to be kind of rare this week, but I expect to see Paul's article about Pluto show up when the newspaper gets back into normal operation here. In another month, we have a meeting on March 10th, business meeting, smorgasbord talks. So plan on what you'd like to share with the rest of us. Let Dino know, and he'll give you some time on the agenda. And we will hope to see you then. Well, until then, keep looking up.
Thanks, Dale.
Thanks, everybody.
Thank you.
Yep.
Yes.
Thank you.
Thank you.
Nice.